Okay, so today I'm going to finish up balloons, and I'm going to try to give you some early material for water distribution with the idea that you'll need it for the problem set. So I don't want to dawdle my way through balloons. I forget each year just how hard it is to present all the material in balloons and sort of underdo it. So let me see if I can do it more efficiently this time. Where things stand, basically. First off, fluids, like gases and liquids, push on things, but describing the push simply in terms of force is kind of messy because fluids push on the entire surface that they're exposed to, and the amount of push, the total overall force that a fluid exerts on the surface depends on the size of the surface. That's not the case with ordinary forces pushing on ordinary objects. When you push on a file cabinet, it doesn't matter whether it's a 2-drawer file cabinet or a 4-drawer. You put 100 Newton force on, you're exerting 100 Newton force on it. But for a gas, the different size file cabinets experience different forces. So to characterize how a fluid pushes on surfaces, or even on itself, we use this quantity known as pressure, which is the force exerted divided by the surface area of which that force is exerted. So it's force per unit of surface area. For example, newtons per square meter, or pounds per square inch is the common one used in the US. So fluids like the air in this room are pushing on every surface, and they're pushing by way of pressure, and the approximate pressure for ordinary air in ordinary situations is about 100,000 newtons per square meter. So on a surface this big, it's pushing very hard. 100,000 newtons is a huge force. I should know it in pounds. It's like 20,000 pounds, give or take, something like that. It's huge. Pounds per square inch, so the square inch is much smaller. The atmosphere pushes with a force of just under 15 pounds on every square inch. So again, a very big force. So you're okay with the idea of pressure, or any questions about the idea of pressure? All right, so I showed you last time with those two hemispheres, the so-called Magdeburg hemispheres, that if you take the air out from inside this clamshell, so that only the outside air is pushing in, nothing's pushing out, they're bound together with a huge force, finally. It's big enough that people can't pull those two spheres apart easily. I mean, really, it's just the limits of what's practical for ordinary people. All right. So where does this huge pressure come from that we're immersed in right now? And it comes from the need to support the atmosphere. The atmosphere down here is supporting the atmosphere overhead. I should say first, to make sure it's clear, that the gas, where does it even get the ability to exert pressure? It's because the air that we're immersed in consists of lots of little particles. Most of them are nitrogen molecules and oxygen molecules. They're traveling very fast with thermal energy. So without thermal energy, the atmosphere would collapse. It's held up by thermal energy. And those little particles are traveling very fast. I said last time, it's about 0.5 kilometer per second. That's for the nitrogens and the oxygens. It turns out that the energy they're carrying, because it's thermal energy, and because it's sort of statistically distributed among the particles, all the particles, on average, carry the same amount of kinetic energy. And so that means that the littler particles, littler being less mass, like a helium atom, which has got a tiny mass, it's a little guy. It's the Mini Cooper amidst the SUVs. In order for it to carry that amount of kinetic energy, it has to travel faster. It's got very little mass, so it compensates by going faster. So a helium atom in this ambient environment around us would be traveling about 1 kilometer per second, considerably faster than the other guys. And that'll come back to be important when I talk about how a helium balloon works. Okay, so you picture these things in frenetic motion. You don't notice this so much because they collide with each other all the time, and they make very little progress. So it's just kind of buzzing around. But you do notice the effects of this behavior when, for example, someone opens a perfume bottle on one side of the room, and a little bit later you start to smell it. How did the particles, those are gas particles from the perfume, how did they drift? Well, that random motion, they eventually make a little progress, and they eventually work their way. Even in still air, they manage to move through the air with this thermal motion. It's called, that process is known as diffusion. So it happens. Okay. That's how the air is working in front of us. And the air around us, given that crazy motion, if it could get away from the Earth, it would, but it can't. It's held down by gravity. So the air the air above us is this large sea of air, where the air down here is supporting the air up there against the crush of gravity, and the air up there is supporting the air above it still and all the way up to the top of the atmosphere. And so there's an overall pressure imbalance between pretty high pressure down here and no pressure up at the top. So that column of air is experiencing a net upward push due to pressure. High pressure here, low pressure there, zero pressure there. That's an upward overall push on this column of air that I hope you can visualize. It's pushed upward by pressure, and it's pulled downward by gravity, by the weight of that column. And they're balanced. In still air, where everything's settled down and no wind and everything like that, it's all in equilibrium. Each portion of air gets an upward net push from pressure that's just right to balance its own weight. And it works all the way up. And the consequence of this is that down here, down low, the air particles are packed tightly, and their pressure is high. The act of packing them tightly, all things being equal, that is the same temperature. That's the all things being equal. Packing them tightly increases their pressure because they hit more often. There's just more of them there to bounce off things and exert their pressure. So the air down here is tightly packed and therefore is dense. Density is mass per volume. So there's a lot of mass per volume here, about 1.25 kilograms per cubic meter. With lots of density, there's also lots of pressure. And it turns out the density and pressure track together if you keep the temperature constant. Don't change the speeds with which these particles are moving. Just increase the number in a box. If you increase the number in a box, which is to say you increase the density, you also increase the pressure by the same factor. Double the density, you double the pressure. Just don't change their speed. Keep them the same temperature. Is that okay? So first observation is the pressure of a gas, keeping temperature constant, keeping the gas constant. Don't swap gases. The pressure is proportional to the density. Double the density, double the pressure. It's a useful observation. It's got somebody's name attached to it. I don't remember whose. But initially it was an empirical result. People measured it and went, wow, look at that. You double the density, you double the pressure. Wow, this is good. I'll put my name on it. It's probably Boyle or somebody like that. Okay. Because of the need for the air down here to support the air above it, which in turn supports the air above that. Do you have a question? How does the air pressure affect our movement? When you're just standing there, you're under enormous pressure on every surface. That is, every surface of you is being pushed inward with a force of, if you want American units, it's 15 pounds per square inch. So this little patch is getting 15 pounds of push in, right? It turns out that we develop pressure inside us, too, that pushes out equally hard. So we don't notice that on our skin. Then the overall pressure force on one side of my face is balanced by an overall pressure force on the other side. It all cancels. It just keeps canceling. Almost. It doesn't quite cancel. I'll come back in a second to why it doesn't. I should do it now. The reason it doesn't quite cancel. Let me get something for me to talk about. So I'll just. So, just like my head a minute ago, now it's the balloon. There's a force inward this direction by virtue of the pressure on this surface. Force inward on this one by virtue of this, the pressure over here on this side. Similarly, there are pressures on the inside pushing out, but let's just pretend this is one solid object. Don't worry about the gas inside. The point of it at the moment is that all the pressure related forces balance, almost. That's the almost. That's the crucial point. they would balance perfectly if the pressure in this room were totally uniform. And for that to happen, the density in this room and temperature would have to be totally uniform. And it's not quite. The temperature's uniform, essentially. But the pressure and density aren't. Why not? Because the air down here has to support the air at the top of the room and everything above. Whereas the air at the top of the room only has to support the air above it. This air down here is a little more dense and therefore a little higher in pressure than the air at the top of the room. Is everybody okay with that idea? You would notice this more dramatically if it weren't air, but rather were water. If you go in water, where the water down here would be supporting the water up there, the stuff's denser. You got to push harder. And if you've gone swimming and gone diving deep into the water, you notice, whoa, the pressure builds up when you go down deep, because the water down there is supporting the water up above it. Okay. So Savannah's observation is if you have to move through the water, things get different than moving through air. Once you start moving, what I've talked about for the moment is just for things sitting still. That there's it turns the pressure's a little higher down low than it is up here. So this balloon is experiencing a little bigger push at the bottom, upward, than it is push at the top, downward. They're unbalanced. That difference produces an upward push on the balloon that's known as the buoyant force. So that's the first observation. That's one for balloons. But if we start making the balloon move through the air, something else happens. We get air resistance. And the air resistance comes about from the interaction between the balloon and the air it bumps into, and then has to get around it. And it leaves behind itself, in fact, a swirling wake of turbulent air. If you've ever watched a car going past a whole bunch of leaves on a fall day, you see this swirling mess of leaves behind the car. The car has really disturbed the air in going through it and has transferred forward momentum to the air. And that's the origin of air resistance. And the momentum it's transferring to the air depends on sort of how much air it bothers and how fast it makes that air go. But air is light, fluffy stuff compared to water. You do the same thing in water, and you stir up the same volume of water and drag it with you. It's way harder. That's a much bigger transfer of momentum. So the water resistance is way worse than air resistance. And we'll get to that when we start talking about how a ball travels in the presence of air. I've talked about balls bouncing. The second part of the ball story is, okay, so what if you throw a ball through the air? And it turns out the ball and the air talk to each other a lot. Okay? Partly that's just a nuisance. It slows the ball down, but it allows you to do cool things like curveballs. Okay? So right now, the air effects that we're looking at are not the ones that are associated with movement, air resistance, but rather the ones that just when you're sitting still, you experience a buoyant force. And the buoyant force comes about because the air density and pressure decrease as you go upward. That's what's known as a gradient. Gradients in physical quantities are continuous evolutions of the value of that physical quantity as you go from place A to place B. And so, I'm telling you this, I'll never test you on it, I don't care. It's a useful name. Gradients show up in other contexts, like the book I have, Gradients in Color, from blue to red or something like that. There are lots of gradients in the world. And so here we have a pressure gradient, also a density gradient. And the official rule is gradients point in the direction of increasing quantity. So it's a pressure gradient downward. It's actually got a direction. And it's a density gradient downward. But I'm just telling you. Yeah? So how can there be a buoyant force if the balloon is at equilibrium? If I fill this balloon with ordinary air and pretend the balloon doesn't have the skin doesn't cause trouble, like doesn't have any weight, doesn't smush the air inside it, make it a little denser than normal, which it does, then so we basically got a balloon-shaped blob of air. I'm going to let go of this balloon and let it My fingers are getting tired. I guess I could tie it off. Rocket propulsion. Okay, so here's the balloon-shaped blob of air. It's perfect, no skin, so the skin doesn't cause any trouble. The pressure and density are perfect. That blob of air, if I let go of it, it doesn't fall. It's perfectly supported. So can you visualize it? If I could fill it with smoke, there it would be, hovering. It weighs something, and yet it's not falling. Something's pushing up on it, and that's the buoyant force. So the air around here each portion is being supported by the air below it and around it. It's experiencing just enough upward force to hold it in place. This air is too, all of it. It's hovering in place. And that's the origin of what's known as Archimedes' principle, which is this, that any object that's immersed in a fluid, in this case a balloon, experiences an upward force that's exactly equal to the weight of the fluid it displaces. So this is one of these great aha moments that Archimedes had 2,000 years ago. That if you look at that balloon-shaped blob of air that I'm pretending exists in my hand, or visualizing, right? It's perfectly supported, so that we know what the upward force is on that balloon-shaped blob of air. It's upward, but equal to the weight of the blob. Is that okay with everybody? Any questions about that idea? So the surrounding air is pushing up on this blob of, in this case, air with a force equal to the weight of that air. If I take that air away and I replace it with anything, a chunk of lead shaped like the blob, the surrounding air doesn't know I swapped it. It's not paying attention. It's just pushing. It doesn't care what it's pushing on. It will still push upward on that blob, now of lead, with a force that's equal to the weight of the air that was pushed out of the way by the blob itself. Yeah? Float, okay. Okay. Savannah's question is, if you have an object that's immersed in a fluid, but not just one fluid, but two, a rubber duck floating on the bathtub water, right? It's displacing partly water and partly air. Does the buoyant force on it, what's Archimedes' principle have to say about that? And the answer is, that rubber duck, when it settles at equilibrium, so it's perfectly supported, no more, no less, is displacing exactly its weight in a mixture of water and air. And it figures it out. It negotiates. If it's too deep in displacing too much water, it's pushing away the water now. You're displacing too much water. It weighs a lot. The buoyant force gets extra strong, and the ducky accelerates up. If it goes too high, so it's not displacing enough water, too much air, it's under-supported. The buoyant force gets smaller. And so things bob up and down. You watch them all, what's the bobbing going on? Why does the wood, some wood floats at different heights and stuff? It's negotiating. It's figuring out exactly what mixture of air and water it needs to displace to exactly support itself, no more, no less. So wood, when it's newly cut and you put it in water, and it weighs relatively little for its volume, assuming it's nice and dry, then it floats high in the water because it does not have to displace very much water to support its own, to develop a buoyant force that supports it. But once it gets waterlogged and its density increases, it has more mass per volume, which also means that it has more weight per volume. It therefore settles lower and lower into the water until finally, when even displacing water 100% doesn't give it enough buoyant force to support its weight, then it settles to the bottom. It goes right down through the water and drops low. Yeah, so when you're floating in water, depending on whether you've taken a big breath of air or not, you float at different heights. You settle just at the right mixture of air and water. Is that okay? Other questions? Let me show you that Archimedes' principle works. Okay. So that guy will look, this is I'm going to try to remember to turn off. This is a cup and a cylinder. The cylinder is sealed and it has a certain volume. The cup has the same volume and therefore can hold the same volume of water as the cylinder is going to displace. Right now, this whole assembly, cylinder and cup, weigh a little over 13 newtons. So 13 times a small apple. I'm going to immerse the cylinder in water. When I do that, the water is going to push up. How hard? It's going to push up with a buoyant force that's equal to the weight of the displaced water, namely the weight of a cylinder-shaped chunk of water. And here we go. So the water is helping to support that cylinder now. There, we got it. And as a result, the scale doesn't have to pull up as hard anymore. So instead of being a little over 13, we're now a little below 10. So it's about 3 3/4 maybe newtons of upward push is being provided not by the scale, but by the water. That's the buoyant force that the water is exerting. Is that okay? And to show you that 3 1/4 Newton upward force is equal to the weight of a cylinder-sized blob of water, I'll fill the cup part with water. Yeah, needed a little more. There we go. Is the cylinder under? Yeah. We're back at a little over 13. So the buoyant force up on the cylinder is exactly the same but upward, as the weight of the cylinder-sized portion of water pulled downward. You okay with what I just demonstrated, I hope? Or questions about it? So Archimedes' principle works. It works so well that not only does it work for an object immersed in a single fluid, but it works for objects immersed in mixtures, as this question brought out. When things sit between two fluids, a liquid, say, and a gas above it, the object goes into equilibrium. When the buoyant force exactly supports it, it needs the right mixture of water and air. Okay? All right, so, of course I put down my reminder without acting on it. Come on, listen to my finger there. All right. So, that's Archimedes' principle. We're now in a position where we can look at why balloons float. And the first one to look at is why a hot air balloon floats. So, if I take an ordinary balloon and fill it with ordinary air, it doesn't float in ordinary air. It doesn't even hover. The reason, in principle, it should hover. If it were a perfectly massless, weightless balloon skin that didn't squish the air, it would hover. But the reality is, balloon skins are dense material. The rubber's denser than any gases. And the other thing is the balloon skin, because it's elastic, it tends to squish the air particles between it. It needs a relentless pressure imbalance pushing outward to keep the balloon skin from collapsing, shrinking the balloon down to nothing, down to its unblown up size. So, an ordinary balloon filled with ordinary air does not float. How can you fix that? Well, you need to reduce the density of the gas inside the balloon. Ordinary air at ordinary temperatures won't do it. So how can you, and I should point out that I'm using the word density. Why does density matter? It turns out that I've talked about if an object immersed in the air weighs the same as the air it displaces, then it hovers. If it weighs more than the air it displaces, it descends. If it weighs less than the air it displaces, it ascends, it goes up, it accelerates upward. That much should already be reasonably clear. Do you have questions about that? Okay. If to get the size of the object out of the story, instead of worrying about the weight of the object, let's talk about the weight of the object per unit of volume. And we don't even need to use the weight. We can use the mass per volume because weight and mass go together, right? They're proportional to each other. So the point of this is this. An object that's immersed in a fluid, if that object has the same density as the fluid, that is the same mass per volume, kilograms per liter or per cubic meter, then the buoyant force will perfectly support it and it will float. It will just hover, okay? If it's more dense than the fluid it displaces, it will descend. Lead, for example, is much more dense than air, and down it goes. If the object is less dense than the air, it will be over-supported by the buoyant force, and it will accelerate upward. So that's the goal for balloons, is to get their density, or at least their average density, even if you take into account that part of them is rubber and part of them is gas. If you take the overall mass and divide it by the overall volume, you get the overall density. You want that density to be less than the density of the surrounding air. That'll do it. Do you follow that? Okay? I mean, tell me if not. Last chance. Okay. So we got to get the density down. How can we do that? Well, one way to do that is to change the speed of the particles in the gas. Stick with air. Use ordinary air, but change the speed with which the particles are moving. If you decrease their speed, they will travel more lethargically, they will hit less often on surfaces, and they will hit more gently, and the pressure will go down. If, on the other hand, you increase the temperature, and therefore their thermal energy, they will travel faster. They will hit more often, and they will hit harder, and transfer more momentum every hit. So temperature, if you leave everything, leave the pressure unchanged. No, I shouldn't. Let me just say, if you just change the temperature, don't do anything else to the gas, leave the same number of particles in a certain location. If you change the temperature, you will change the pressure. Lowering the temperature reduces the pressure, increasing the temperature increases the pressure. Before going toward the hot end, let me go toward the cold end. And I'm going to bring some balloons over with me. Little ones make life easier. This room, it's ordinary room temperature you think of. The temperature that matters for this kind of a story is not temperature on the Fahrenheit scale or the Celsius scale, as I've talked about last time, but rather a scale in which the zero of the temperature scale corresponds to the bottom of temperature, the point at which there's no thermal energy available anymore in the material. And we can go 3/4 of the way towards that real zero, what's known as absolute zero, by working with a liquefied gas. In this case, it's liquid nitrogen. And my rule of thumb is any excuse for playing with liquid nitrogen is a good excuse. So this stuff, you guys may have encountered this in various contexts, like burning off warts and stuff. This stuff is very cold. I poured it into this glass container, which is actually a thermos, an unmirrored thermos bottle, and it considers that glass at room temperature as exquisitely hot. So it's like pouring water on a hot frying pan. And the same thing happens if I pour this stuff on the floor. It skittles around on the floor like water on a hot frying pan, and it's the little balls. After class, you can come and play with this stuff. Just don't get on your skin to sit there for a while, otherwise you'll be burning, you'll be killing the skin. Instant frostbite, it's great, right? But these little balls skittle around there like water on a hot frying pan, and they pick up all the dust. So they end up carrying around the dust around the room, which is always fun. All right, so real cold there. 3/4 of the way to the 3/4, yeah, what did I say? 3/4 of the way to absolute zero. And if I take a balloon, this is a tank full of helium. And just to make sure you know that it's helium,
hello, this is me talking normally, and I just sound totally normal, right? Nothing different. We'll talk. The speed of sound is actually much faster in helium than in air. So all the resonances in my vocal system go way up. And yeah, I got to make sure I breathe it out because there's no oxygen in it. Come on, this is too hard. Bigger balloon. I want to keep it small enough that I can get it into this is called the Dewar flask, after the James Dewar who invented it. It's double walled with a vacuum in between. The point of that is that it's trying to make it hard for heat to flow in through the surfaces into that liquid so the liquid doesn't boil all that fast. Now, this balloon right now has air trapped inside, a certain number of air molecules. They are at the same temperature as the outside air and approximately the same pressure. It's a little higher than outside because of the stretchiness of the balloon, but basically normal density, normal pressure, normal temperature inside there. And there it is. If I reduce the temperature by a factor of 4 by putting in liquid nitrogen, the particles will slow down and they will produce much less pressure. And I can't let the pressure won't just drop inside that balloon without consequences. The balloon will shrink in size because the surrounding air will just squish it, going, wow, nobody's pushing back very hard. I'll just push the sides in. And the consequence of cooling the gas inside that balloon to 1/4 its original temperature is that it shrinks to about 1/4 its original volume. The particles just pack more tightly to work better as a team to maintain ordinary pressure. So now the gas inside is down by a factor of 4 in temperature. It's going up by a factor of 4 in density to compensate. It's packed 4 times as tight. So there's the balloon. And while it's packed tightly, it doesn't float. But once it unpacks by going back to room temperature and expanding, it'll probably, I didn't make it very big, so it might just barely lift off. Go. It's sitting on the last little tip of its rubber. You can do it, boy. You can do it. Yeah. Right? Now, the reason I used helium for that demonstration, the point of the demonstration, apart from giving you something to watch other than me, is that when you cool down the gas and keep its pressure the same, which is what happened because the balloon changes shape to balance the pressure. When you cool it down by a factor of 4, the density has to go up by a factor of 4 to compensate. That works fine for helium, but if I try to do that for air, I can use a smaller balloon now. If I try to do it for air, something bad happens as the gas gets smaller. Actually, let me do it in the big balloon. I keep changing my mind. Okay. If I do the same story now with air instead of helium, and I put it in, you think, well, it should go down to 1/4 its original volume. But a catastrophe occurs, and that is that the air molecules begin to stick to one another, and they stop being a gas. The air liquefies. So this balloon now is getting way small because the air inside isn't just shrinking to a smaller blob of denser air, it's turning all the way into a liquid. What always amazes me is balloons will tolerate this abuse. I froze it to incredibly low temperature, and it just takes a beating and keeps going. So that balloon started with a certain amount of air, and it shrunk dramatically because it liquefied, and now it's unliquefying. This time I'm not going to seal it off. I will shrink the air, first by a factor of 4, and then as it liquefies by a bigger factor even than that. And then I'll add more air. And I'll shrink it again. And then I'll add more. 3. 4. You know where this is going, don't you? 5.
5. Six. It's 10 I got to get to. 7. 8. 9. 10. 'If I don't go up to 10, it sits there like the rest of class waiting to explode. It's already doing bad. Come on, it's time. Ugh. Oh, come on. All right. So that was going cold. The air went, to maintain the same pressure as the surrounding air, it had to become more dense, and therefore it would sink even worse. How about let's go to the other direction. We'll go to hotter air. The air particles are traveling faster and hitting more often, hitting harder, and it takes fewer of them in a given volume to have atmospheric pressure. So we can have a balloon that's inflated, in effect, with only a few particles traveling very hard and very fast and maintaining the pressure enough to keep the surrounding air from squeezing the balloon away. So this is a fiercely hot, it's not a hair dryer. It's a hair dryer if you have wire bristles for hair. So the point is I'm gonna put hot, ordinary air into this. Is it hot? There, yes, it's hot. Ordinary air into this balloon, but it's hot air. And as a result, the particles are traveling faster, hitting more often, and we don't need as many air particles in this balloon as we would to fill it with ordinary room temperature air. So let me get it nice and full of warm air, hot air. And off it goes. So it's got a lower density gas inside, namely hot air. Fewer particles doing the job of less particles if it were cooler. You okay with the idea, why that worked? Questions? So that's one way in which to make a gas that has a lower density. I just want to get it safely out of the way. A lower density than the surrounding air. Heat the air up, the particles spread out. There are not as many of them per liter, and it weighs less than the buoyant force it experiences, and up it goes. The other way to do it is to use tinier particles. We've already talked about that. To use particles that have less mass, and that's the story of helium. Helium, one more balloon, but I'll fill it properly. Helium, the particles in helium are tiny. They're 1/7 approximately the mass of a nitrogen molecule. And therefore, when I fill this balloon full of helium particles, the particles are traveling faster and hitting more often, and they make up for their tininess by producing the same pressure as the same it's the same number of air molecules. So let me just seal this off and talk about it, and then I'll let go of it. If I had the same balloon full not of helium but of air next to it, they would contain the same number of particles. If you count them, it's a huge number. Remember Avogadro's number? I mean, there's something like Avogadro's number of helium atoms in there. But if I had an air balloon, the same size, same situation, it would have the same number of particles. Okay? What are the consequences of that? Well, the air particles, each one weighs 7 times as much on average as the heliums. So the balloon would weigh essentially 7 times as much being full of air as it does being full of helium. You okay with that idea? So it turns out that the pressure of a gas depends not on what specific particles you're using, but rather how dense those particles are, what's known as particle density. It's a peculiar quantity that shows up really only in this context. So particle density. The particles per volume. The pressure of a gas depends on the particle density, how many particles there are per volume, and the temperature. So it doesn't matter whether they're helium particles or air particles. They count the same. They have the same effect, and this gives rise to what's known as the ideal gas law. So this is neglecting things like the fact that air liquefies if you cool it too much. The ideal gas law makes the following observation. It says that the pressure of a gas depends on only 2 things and a fundamental constant of nature. The Boltzmann constant is a fundamental constant of nature. The pressure of the gas depends on 2 things. The particle density, that's how many particles there are per liter, and the temperature measured on an absolute temperature scale, where 0 is a real 0. And so this balloon contains the right number of particles at room temperature to have atmospheric pressure. If it had more particles packed into that balloon, it would have more pressure, and the balloon would swell. If it had too few particles packed into that, it would have less than atmospheric pressure, and the balloon would smush. So it's just right. It's got the right particle density to match atmospheric pressure. In fact, it's got the same particle density as the air here. The difference is those particles weigh so little that the buoyant force on this is way less than its weight. When I let go of it, boop, up it goes. And it'll stay up. And you know, it'll stay up there for the rest of the day, but tomorrow it'll be on the ground. And that's because those particles, those helium particles, they're traveling very fast, and they can work their way between the rubber molecules, and they diffuse through it. It's also diffusion. They migrate through, and they're leaking out right through the walls of the balloon, and they come out of rubber balloons sort of on a 1-day time scale. On the fancy Mylar ones, the plastic sheet balloons that you get for graduation that people are constantly losing while trying to walk the lawn, off goes another one. Pink flamingo, up it goes. Those guys will hold the helium in pretty well for a week or 2 or something like that. All right? Helium, however, is not the only lighter than air gas, lighter than air. Hydrogen's a famous one, right? Hydrogen's about half the weight. A hydrogen molecule weighs about half as much as a helium molecule, so the balloon will float a little bit better. It weighs a little closer to nothing than helium does. But another familiar gas that is lighter than air, that has a lower density than air, is methane, also commercially available as natural gas. So who wants to help me light methane bubbles? Victoria? So here's the deal. I have a ready supply of methane coming to us from the gas company. And Victoria's task is going to be to, as the bubbles go by, I'll blow them, you light them.
Wait, so
You hold this down there. I'm going to make the bubbles float by there, and you chase them and catch them on fire. Just don't catch me on fire, okay? Yep. I'm going to blow soap bubbles. Yes, you'll have to touch the bubbles. Just not while I'm blowing it up. They get away from time to time. And even if they pop, the bubble is still there. It just doesn't have a shell on it. You can still light it. One more. Woo. Okay. So, story with that is one of my high school classmates would blow up big dry cleaning bags. You need a very, very light bag, not heavy rubber. Light dry cleaning bag. He would blow it up with natural gas or hydrogen, depending on what time, and put a fuse on it, basically. And then he would listen on his police scanners for all the UFO reports. All right. So that's the story of balloons. The idea is to make the balloon less dense than the surrounding air, and up it goes. I do want to say 2 cents about water, because it's important for the story of, okay, it's important for the problem set. First off, the air down here is supporting the air up there. This column of air from here to the top of the atmosphere is supported by a pressure imbalance between atmospheric pressure down here and zero pressure up there. But air is light, fluffy stuff. You can support a 5-10 kilometer column of air. It's very tall. It gets thinner at the top, but it's a huge, giant column of air that is supported by this difference in pressure. Atmospheric at the bottom, nothing at the top. That's an upward imbalance that pushes up, right? If it were water, it would be a shorter column. You can't support a column that's 10, 20 kilometers tall. It's much shorter. How short? We'll play with this next time. It's about 30 feet. That's as high as you can support. Atmospheric pressure can support that column when there's no pressure above it. If you reduce the pressure a little bit, you can support a column that's shorter. So when you drink from a straw, right now, the water is held up in the straw by a pressure imbalance. Atmospheric down here, a little less than atmosphere where my finger's sealing it. There's gas in there a little bit, and it's less than atmospheric pressure. So it's that pressure imbalance that's holding water up in a straw. You okay with that idea? If I let atmospheric pressure enter the top of the straw, the water falls out. So when you're drinking from a straw, you're not attracting water to your mouth. You're simply allowing atmospheric pressure to push the water up the straw. And the higher the atmospheric pressure is, and the lower the pressure at the top is, the bigger the pressure imbalance, and the taller the column of water that this difference can support. Can you picture that? The bigger the pressure at the bottom, and the lower the pressure at the top, the taller the column can get and be supported. If it's water, you can get about 30 feet here on Earth, the ordinary pressure. If it's mercury, which is much denser, you can only pull up about 30 inches. That's a 30-inch column is about all that the Earth's atmosphere can support, with full atmosphere at the bottom, nothing at the top. And that's what they report barometric pressure often is 30 inches of mercury. Have you ever heard that? That's telling you how much the ambient atmosphere can push up as a column when there's nothing pushing down. Okay? So atmospheric pressure matters. That's one of the problem set problems. The other question is when water goes through a system, flows through a system, it can have energy in various forms. In the present situation, there is water sitting here in this container. There's a hose attached to the container, and there is a nozzle sitting at the end right there. And right now, the water has energy. It's not moving, so no kinetic energy. It's at room pressure, which we can pretend is zero because there's nothing lower than room pressure available with no vacuum pump around. So it's got no pressure, no energy available in its motion. It's got no energy available in its pressure at the top here, but it has energy available in its gravitational potential energy. And I just did work on it, and I added energy to it. So it now has extra energy in the form of gravitational. So its total energy in these ordered forms of energy, gravitational, kinetic, and energy associated with pressure, it's all gravitational here. When I let this nozzle go out, it's going to do the following. It's going to take the gravitational potential energy, it's going to turn it gradually into pressure energy as it descends. The pressure is going to get As it gets lower, it's going to lose gravitational potential energy because it's lower. Where did the energy go? Energy is conserved. It's going to become associated with pressure. And I need to talk more about that, and I will next time. So the pressure gets high here. And then it goes to this nozzle, and the nozzle's job is to turn energy associated with pressure into energy associated with motion, kinetic. And the water will spray. There it goes. And actually, it can spray back to its original height, almost exactly. Why? Because the energy is going from gravitational to pressure to kinetic back to gravitational. You'll never see the water go higher than this, though. It can't. It doesn't have the energy to go higher. The best it can do is go from where it started, energy, it's all energy in its height. All energy in its pressure, all energy in its motion, all energy in its height. It can only go back to where it started from. And it doesn't even manage to do that quite right because it's wasting some of its energy, which is another part of the story. So having told you that, you can answer the last of the problem set problems. Thanks for sticking around. And if you want to come play with liquid nitrogen or light bubbles, come on up.